Welcome back again. Today we are going to discuss some exercise problems from chapter 5 of your textbook. These are based on permutation groups, and let us see how much we can cover. Okay, and the rest of questions we can see later on, maybe in the next week. Okay, after the test. So question number 1, this tells that if alpha and beta, the given permutations, then we need to compute the inverse and the product of them. So before starting, we should note it down that suppose if we are writing that some f is a function from a set A to, for example, here A to A, and both are finite sets. Okay, and then x is some element from A. This will be mapped onto fx, and sometimes we used to write like this. Okay, y equals to fx. And if this is a 1 1 and onto, because permutations are nothing but 1 1 onto maps, so we can talk about inverse of function. So we can write f inverse of x equals to y. So for example, if we take f inverse, suppose we are denoting f inverse by z, then in this case we can write f g of x equals to y. So what we are doing, we are just changing the role of image and pre-image. Okay, so this was the image and this was the pre-image. Now it has become pre-image. I think I wrote, so I did something. Okay, I should write here fy and here x. Okay, so here g of x, g of y, in fact g of y is equals to x. So we have changed the role of x and y. Thing is that, so in this sense, if you see the permutation in the first row, we find that they are members from domain. These are the members from domain. That is, if you are writing 1, 2, 3, something like this, and then this is mapped onto 2, and 2 is mapped onto 1, and then 3 is fixed, something like this. Okay, so this is a pre-image. These are the pre-images, and these are the images. Now we will change the role. We will swap these two. Okay, so this is natural to write alpha inverse equals to. Let us change the role. So you can write the bottom in the top. So we can write 2, 1, 3, 5, 4, 6. I'm just telling you a simple method how to do this one. Okay, and then you can write 1, 2, 3, and then 4, 5, and 6. You should note one thing always, that you have to take care of image, the elements and images of that particular element. So here you see 2 was the image of 1. So I have so this now became pre-image, and 1 has become image. So like this. Okay, so this is the inverse. Of course, you can write them in product of cycle. So from 2 it is starting 2 and ending 2. So 2 goes to 1 and 1 goes to 2. This is a one cycle, and then you can write 3. Of course, single cycle can be skipped, but let us write them. And then 5 goes to 4, 5 goes to 4, and 4 goes to 5, and then we have 6 also. Okay, then we can write, because single cycle can be skipped. So we have a 2, 1, and 5 and 4. Fine. And of course, these two are disjoint cycles. So we very much can write 5, 4, 2, 1. There is no problem. Fine. I guess you got how to find the inverse. Okay. So rest thing, that is if you want to find a beta alpha and alpha beta, I think you can do. So let me find that out one for you. If you are writing alpha beta, So what we will write this one for left in the left and this is in the right. So 1 goes to 6, 1 goes to 6, and 6 goes to 6 in the alpha. Okay, let us take 2. 2 goes to 1, and then 1 goes to 2. So 2 is fixed here. Okay, and then 3 map to 2 and 2 map to 1, and then 4 is fixed here. You see 4 is fixed here, and 4 goes to 5 here. 4 goes to 4 and 4 goes to 5, and then we have 5 goes to 3, and then let us see 3 goes to 3. So 5 is 3, 5 goes to 3, and then we are left with 6 goes to 5, 6 goes to 5, and then we need to search 5 goes to 4. Okay, so you should remember that when you are writing some permutation like this, every element 1 2 3 4 5 6 must appear only once. They should not be repeated here. Okay, so 1 2 3 4 5 6 in the first row, there is no problem, and in the bottom you should check after finding their product that is there anything repeating or anything missing. So that need to be taken care. So 1 2 3 4 5 and 6. So there is a least possibility that you have done something wrong. Okay, so similarly you can find beta and alpha also, and of course you can write down them as a product of cycles. So you can start with any element, there is no problem. 1 goes to 6, 6 goes to 4, 1 goes to 6, 6 goes to 4, and then 4 goes to 5, and then 5 goes to 3, and 3 to 1. Fine. So of course we are not supposed to write 1. So this is one cycle, and see if there is something left in this. Is anything missing? 1, I think 2 is missing, and because 2 is fixed here. Okay, so you can write like this, but thing is that single cycle can be skipped always. So you can write it 1 6 4 and then 5 and then 3. Okay, you can start writing from here also, there is no problem. If you would have taken 4 initially, then you can write 4, then 5, 5, then 3, 3 to 1, and 1 to 6, and 6 to 4. So like this. Okay, so if you are starting writing it with 4, so 4, 5, 3, 1, and 6, both are the same only. So let us see the next question. Question number 2. There are 2 permutations, alpha and beta, and then we need to write them in 2 ways. First, product of disjoint cycles, and then a product of 2 cycles. Fine. So these are the applications, in fact, of theorems we studied in properties of permutation, that every permutation can be written as product of disjoint cycles. And also we have proved a result that every permutation can be also written as product of 2 cycles. Okay, so let us write one thing, that is alpha. Let us take alpha. So alpha, we need to write it as a product of disjoint cycle. So you can start with some element, you can take anything, but let us take 1. So 1 goes to 2, and 2 goes to 3, then search for 3, 3 goes to 4, 4 goes to 5, 5 goes to 1. So we started with 1, and we are ending here. We are arriving at 1. Okay, so what we should write 1, and then 2, then 3, then 4, then 5. So this completes one cycle. Then let us search for the another cycle. 6 goes to 7, 7 goes to 8, and 8 goes to 6. So we again start with 6. We are starting with 6 here and ending at 6. So 6, 7, and then 8. Fine. So 3 members, 3 symbols are there. So 1 2 3 4 5 6 4 5, and then 6 7 8. Fine. So they are, of course, they are disjoint cycles. You can see that there is nothing common. Fine. So this is the one. This is the first part, solution of first part. You can write. But thing is that in the second part, they are asking that you should write that this alpha as a product of disjoint. Product of 2 cycles. So alpha, once we have written like this, we can use this to write as product of two cycles. So how we can write 1 5, start here and then take this one 1 5, then 1 4, then 1 3, and then 1 2. This is one way. So there are so many ways, in fact infinite many number of ways to write in terms of product. Okay, so if the cycle is very lengthy, then so the thing is that there may be so many ways, not unique ways. And I say the infinite ways, it means that I'm talking about it depends on the cycle, how much length the cycle is. Fine. So there product, if you are writing some permutation in form of product of two cycles, then the two cycle product representation may not be unique. Fine. I may write something else, you may write something else. Okay, you may simply swap these two to one something. Okay, and then okay, then we can write 6 8 and then 6 7. Fine. So this is one way how we can write. Fine. So of course from here you can very much compute so many things. You can compute the order of alpha, you can also compute the nature of alpha, whether it is even or odd. Okay, so similarly you can also write beta. If you are taking beta, so beta is you can write the product as product of disjoint cycle. So we have one. Okay, one is fixed. If you are taking 2, so 2 goes to 3, 2 goes to 3, 3 goes to 8, and then search for 8, 8 gives to 4, and then 4 goes to 7, 7 goes to 2. So we started with 2 and arriving at 2. So 2 and then 3 and then 8. Okay, and then after 8 we have 4 and then 4 and then we have 7 and then 7. After 7 we have 2. Okay, so what left? What symbols are left? Which symbols are left? I guess 1 2 3 4, I think 5. Okay, so once you got one symbol is left, then you can very much write, and then you can start with that one. So 5 goes to 6, 6 goes to 5. So this 5 6, or even you can write 6 5. Okay, what else? I think everything is there. 1 and then 2 3 and then 4 5 6 7 and 8. All 8 symbols are fine. And then similarly as before, we can write them as a product of two cycles. So of course a single cycle can be skipped. So the second cycle, this one, we can write a 2 7 and then 2 4 and then 2 8 and then 2 3. And of course 5 6 is itself a two cycle. Fine. So this is how we can write. And similarly you can find the product of alpha and beta, and then you can write down them as a product of two disjoint cycles. Of course this is easy because once you have written like this, okay, and then you have written like this, but thing is that you may be getting some elements common, some symbols common in these two. It is not like that you have written this as a disjoint cycle, alpha is disjoint cycle, and then beta also disjoint cycle, and you are multiplying these two to get the disjoint cycle representation of alpha and beta. It is not like that, because you see so many things are common in these two. Okay, so that need to be taken care. In fact, you need to multiply first, and then you need to find out what are the disjoint cycles, so that we can write them as a product of these disjoint cycles, and then you can find out the product of two cycles. Okay, fine. Of course these two will work, there is no problem. In here in the second case, this may work. You can write directly alpha representation of two cycle representation of alpha and then beta, one by one you can write like this. Okay, there is no problem. Okay, because you know that a permutation is either even or odd. It cannot be both at once. Fine. Okay, so let us see the question number 3. This says that write each of the following permutation as a product of disjoint cycle. So similar question. Okay. Of course, let me take the first one. 1 2 3 and 5, and then 4 1 and 3. So you need to see really if there is something common. Yeah, there is common. I think 3 is common, 1 is common. So in that case, you need to write first product of these. Okay. So you can start with 1. You can take 1 in the rightmost. So 1. Okay. And then 1 goes to 3. You can find out image of 3 here. Okay. 1 goes to 3, 3 goes to 5. So 1 goes to 5. So 2 is not there, so 2 is fixed. 2 is not there, so 2 is fixed. 2 goes to 2 and 2 goes to 3 here. 2 goes to 3. And then 3 goes to 4 and 4 is fixed. So 4 goes to 4. And then you can write 4 goes to 1 and 1 goes to 2. Fine. And then what we have, we are left. Thing is that you need to exhaust all symbols appearing here. I think you can see very much 1, 2, 3, 4, 5 up to 5. We don't care about the symbol which are not appearing. Of course, they are, if at all they are not appearing, it may be this may be member of, suppose for example, S8. But thing is that S8 or S9, fine. But thing is that you need to see what symbols are appearing. Suppose for example it is from S8, this is from S8, it means that 6, 7 and 8, these are fixed, fine, these are fixed, that's why they have not been written. But it doesn't matter whether it is from S8 or this is from S5, okay, or S9 or whatever be. But thing is that you need to take care the symbol which are appearing here. So okay, 4 goes to 2, and then we need to see 5. 5 is fixed here, okay, and then 5 goes to 5. 5 goes to 1. 5 goes to 1. I think all symbol exhausted. Okay, and then okay, so we can very much write it as in cyclic form. I think it is in cyclic form. So 1 goes to 5. 1 goes to 5. You can start 1 goes to 5. 5 goes to 1. Okay. So 1, 5 first cycle, and then you can 2, 3, 3, 4, 4, 2. So 2, 3, and 4. So this is the product of disjoint cycles. Similarly, you can multiply these 3 components, and then you can write it down. Okay. For this one, C part, if you are writing 1, 2, and then 1, 3, okay, and then 2, 3 is there, then 1, 4, 2 is there. So something you can do, simplify these two. Of course, you can write like this, 1, and then what you can write, 1, 3, and 2. Okay, 1, 3, 2. This you can write 1, 3, 2, and then 2, 3, and then 1, 4, 2. So this makes only 3 cycles, and then you can multiply them. Okay. So let us see next question. Question number 4. Question number 4 says that to find the order of each following permutations. Okay. So we are going to use a result that the result is that if CR is a cycle of length R, then order of CR is R. Fine. So this is the thing, and then another thing we can I think that thing will be used in the next theorem about if alpha and there is this is a product of a CI where I from 1 to R. Okay, and CI are disjoint cycles. With order of CI equals to DI, then order of alpha equals to least common multiple of DI. Okay, so these two results we proved already while we were discussing theory part. So it is very much easy to find the order of each of these. So order of this is what? Anyone? 2. This is 2 cycle. Order of this
3.
And order of this
5.
5.
this is 5. Okay. And order of this is k.
K.
A.
So this is we are able to write because you know they are already written as they are, in fact they are only one product, only one cycle. Okay, if there are so many cycles, they are product of cycles, then we need to use the second result, this result. Okay, so this situation will arise in the next question number 5. What is the order of each of the following permutation? So we will be using the second result, what I just mentioned. For this, we need to first very carefully see whether the permutation, whether the cycle are disjoint or not. So in this case, in first case, 1, 2, 4 and 3, 5, 7. So I think they are disjoint. There is nothing common. So order of this is what? LCM. So order of this is 3 and this is 3. So LCM of 3 and 3, this is going to be 3. Fine. And then you can see the second one, 1, 2, 4 and 3, 5, 6, 7. So here also it very much clear that both are the disjoint cycles. So order of first cycle is 3 and then second one is 4. So what is this? 12. Okay, and then next, what about C? What about C? They are also
6.
disjoint. So 6. And what about this one? 1, 2, 4, and then we have 3, 5, 7, 8, 6, 9. I think they are also disjoint. So LCM of 3 and then 1, 2, 3, 4, 5, 6, and then 6. Tell me the value.
6.
6. Okay. Then let us take up the E, part E. 1, 2, 3, 5, and then we have 2, 4, 5, 6, 7. Okay. So this is not straightforward. So in this case, we need to find a disjoint cycle representation of this. Okay. So how we can write E part? Let us write this 1, 2, 3, and 5, and then we have 2 and 4, 5, then 6 and 7. Okay. So to write them as a disjoint cycle, we need to find the product really. Okay. But okay, and you know how to write how to find the product. Okay. So let us see. 1 is not there, so 1 is fixed. Okay. So 1 goes to 1, 1 goes to 2. Let us see quickly. So and 2 goes to 4, 4 is fixed in the left. Okay, and then 3 is not there, so 3 is fixed. 3 goes to 5, and then 4 goes to 5, and 5 goes to 1, and then 5 goes to 6. 6 is fixed. Okay, and then what we have? We have 7. 7 goes to 2. 2 goes to 3. I think 1, 2, 3, 4, 5. I think we missed 6. Huh? Okay, 6. 6 goes to 7, and 7 goes to here. 7 is fixed. Okay, 6 goes to 7. So you can see 1, 2, 3, 4, 5, 6, 7, 6. Okay, doesn't matter if 7 you have written 7 before 6. There is no problem. Here also you can see 2, 4, 5, nothing is repeating. So you can write them this like as a cycle in form of product of disjoint cycle. So 1 goes to 2, 2 goes to 4, 4 goes to 1. So 1, 4, 1 to 4, 1 to 4, one cycle. So we have we done with the 1 and then 2, then 4, 3 things. And then let us see 3. 3 goes to 5, and then 5 goes to 6. 6 goes to 7, and then 7 goes to 3. So we have written this as a product of disjoint cycles. You can see in these two cycles there is nothing, no symbol common. Okay, so of course the order of this 1 2 4 and then 3 5 6 and 7, order of this is equals to LCM, least common multiple of the order of first, that is 3, and then the order of 7, that is 4. Okay, so this is going to be 12. So similarly you can um, find out the order of F. Okay, so this F you can write like 2 5 and then 3 4. Okay, you can verify it, and then in this case the order of this product would be LCM of 2 and 2. This is going to be 2. Fine. Let us see next question. Question number 6. What is the order of each permutations? So they have given in this is in different form. So what you need to do? You need to first write or decompose them as a disjoint cycle. Okay. So 1 goes to 2, 2 goes to 1. So 1, 2, first one, and then 3, 5, 5, 6, 6, 3. Then 3, 5, and 6. Okay. And then 4 is fixed. 4 is fixed. Okay. So what is the order in this case? LCM of 2 and 3. 6. Fine. And similarly, you can write this also. 1 goes to 7, 7, 1, 7, and then 5, 5, 3, and then 3, 2, 1. So this one. And then what we can take 2, 2, 2, 6, 6, 4, 6, 4, and then 4, 4, 2. Okay. Anything missing? I think 7. Okay, so we can take 7. 7 goes to 5, and 5, 5. 7 goes to 5. 5 goes to 3. No, 7 is there already, so we need not to take this. Okay. 1 and then 2, 3, and then 4, and then 5 and 6, 7. Everything is there. Okay. So order of this LCM of 4 and 3. This is equals to 12. Fine. Let us see next question. Question number 7. What is the order of a product of a pair of disjoint cycles of length 4 and 6? Okay. So let alpha equals to C1 and C2, where length of, that is the length of C1, where length of C1, that is C1, order of C1 is 6, and if length of some cycle is 4 and 6, fine, so their order will be the same number. So order of C1 is 4 and order of C2 is 6. Okay, and they are disjoint moreover. So order of alpha equals to LCM of 4 and 6. So this is going to be 12. Question number 8. Show that A8 contains an element of order 50. So how you can proceed to find this one or to prove this one? Question number 8. It says that A8. Yesterday we have discussed SN, fine, and then its AN as its subgroup. Okay, and also we noted down that order of AN is equals to n factorial by 2. That is order of SN divided by 2. That is AN contains exactly half number of elements of SN. Okay, and AN is the collection of all even permutations in SN. Okay, so A8 essentially, A8, if we are talking about A8, then it has order 8 factorial by 2. In fact, SN has so many elements. If you simply compute this one, S5, so there would be 120 element. In S4, there would be 24 elements. Okay, this is factorial 4. And this is factorial 5. So this is this is a group which rapidly increases the number of elements as n grows. Okay, so let us see how we can it A8 contains an element of order 15. Okay, so how we can write? We need not to prove that it contains an element of order 15, but we need to just write this is the element of this. Okay, so suppose alpha is some element. Okay, and then this is a product of two disjoint cycles. Okay, then these two are disjoint, 2 or 3 disjoint cycles, whatever you feel like you can write, there is no problem. Okay, fine. So such that alpha, order of alpha is equals to 15. So alpha we can take just like this 1, 2, 3, and then another element we can take 4, 5, 6, 7, 8. So these two are disjoint cycles. This is and this also. These two are disjoint cycle. Order of this is 3 and order of this is 5. So LCM of 3 and 5 equals to 15. Okay. So this is a member of if A8. How you can verify that it is a member of A8? This would be an even cycle, even permutation. Okay. So because this is there are 3 symbols in this cycle, so this is going to be even. Okay, and there are also odd number of symbols, so this is also going to be an even permutation. Okay, so sum of 2 even is also even, or else we can say like this. You can write a 1, 2, 3. How you can write 1, 3 and 1, 2. Okay, and then 4, 5, 6, 7, 8. Similar way, you can write 4 and then 8, 4, 7, 4, 6, and 4, 5. So how many numbers? There are 2 numbers, 1, 2, 3, 4, 5, 6. So this is even permutation. So certainly this is going to be in 8, A8. Okay. This was a simple case. This was a simple case, in fact. Okay. This was a simple case we have taken, but in other cases I will explain how we can get the possible order of elements in a group, in a subgroup, or in SN. Okay, so that I will explain. For this, let us take question number 9. Question number 9. Question number 9. This says that what are the possible order for elements in S6 and A6. Okay, I think, okay, just a minute. I think we need to go to next page. Let us go to next page. Here I can start here fresh. Okay, so we are which question we are going to take up now? I think 6th, 7th, 9th question. We are going to take up 9th question. Okay, so 9th question. Question number 9. We need to talk about A6 and S6 and A6, and A6 is a subgroup of S6. Fine. So to find the order of element, possible order of element in S6 and A6, we need to find the partition of 6. And how we are computing the order, that matters a lot. Suppose alpha is some permutation in Sn. Suppose alpha is some permutation Sn. Then we can write alpha as a product of disjoint cycles C1, C2, C3 up to finite number of disjoint cycles. Fine. And then how we define the order of this alpha? LCM of di I from 1 to 3 up to R. Okay. So and di order of C1 is D1, order of D2 C2 is D2, and order of this is C3 D3, and order of CR is DR. Okay. So these are the order of disjoint cycles. Okay. So this is what we are going to take up. So let us take partition of 6 partition of 6. We take this one partition 6 and then we find the partition of this. So how partition means how we can write 6. So we can write 6 as 6. We can write 6 plus 1 there because in S6 there are 6 symbols. So, this is 5 plus 5 1 5 1. Okay, not 6 1. This is 5 1. Okay. Partition function we are talking about P of n, and this is equals to number of partition of n. Okay, just like P of 1 we can write in one ways. P of 2 we can write in two ways, 1 and 2, 1 plus 1 and 2 ways. Okay, like this. Okay, so if we can have a 6 cycle in SN, we can have a 6 cycle, we can have a 5 cycle and a 1 single cycle. Then we can have 5, not 5, but in fact 4 2. We can have a 4 cycle and 1 2 cycle. We can have 4 cycle and 2 single cycle. Then we can have 3 cycle, 2 3 cycles. So 1 3 cycle, 1 2 cycle, 1 single cycle. The elements, the element alpha in Sn, in fact in S6 has these many possibilities. There may be 1 single cycle, there may be in that element there may be 1 5 cycle and 1 cycle. Okay, and then we can have 1 3 cycle, and then break this 1 1 and 1. Okay, like this, and then we can have a 2 3 2 cycle, 2 2 2, and then we can have 2 cycle and 2 single cycle, and then we can have 1 single cycle, and then 1 2 cycle, and then 2 and 4 single cycle. Okay, and then we can have all single cycle. That is, all elements are fixed. And this is the case where if all elements are fixed, it means we are talking about identity. And then we can talk about the order. Okay, so if there is 6 cycle order, what will be the order? 6. There is 1 5 cycle and 1 cycle, and note down that there are possibilities like this C1 C2 C3. Okay, so they are disjoint. Okay, so LCM of 5, if 5 cycle is there, so order of this will be 5, and the single cycle order of single cycle will be 1. So LCM of these two 5, and 4 2, a cycle of length 4, a cycle of length 2. This is 4, and this is also 4. This is 3, and this is 6. This is 3. This is 2, and then this is 2. This is 2, and this is identity. Nothing but identity. All elements are fixed. Single cycle, like you are writing 1 and then 2, then 3, something like this. Okay, up to 6. So every element is fixed here. Okay. So you can see the order of if we have a cycle of this form, then order of this will be 6. If we have a permutation of this form in which we have 1 cycle, 1 5 cycle, and 1 single cycle, so we have order in that case 5. Okay. For example, you can take this one. if you are having suppose a cycle of one cycle of length 5, A, B, C, and D and E, 5, okay, and then one single cycle is there. So how do we do the order of this one? This is cycle length of cycle. This cycle is 5. So order of this element or this permutation is going to be 5. Similarly, if you have 4 A, B, C, and D, and another cycle we have E and F. Okay. So this is a 4 cycle. This is 2 cycle. They are disjoint. Of course, this should be disjoint. We are considering that only. So order of this will be 4. So similarly, we can find out others also. Okay. So these are the order of elements in S6. Fine. So possible orders of elements in S6. What are the order? 1, 2, you can see here 1, 2, and then 3, and then 4, and then 5 and 6. These are the possible orders of elements in S6. Okay. Now next question was that, and the second part, that possible orders of elements in A6. Possible orders of elements in A6. Okay. I think it is not visible. Okay. Possible order. Elements in A6. And do remember that A6 contains only even permutations. A6 contains only even permutation. So we need to find if these are the categories, these are the category of element which can be member of S6. So we need to find which of them can be an even permutation. Okay. So if we have a cycle of length 6, is it even? Anyone? Like A, B, C, D, E, and F. We have written 6. Okay, 6 different distinct symbols are there. So how you can write? You can pair up A, F, A, E, A, D, A, C, and A, B. So how many? 1, 2, 3, 4, and 5. So if there are 1, and then 2, then 3, then 4, then 5. Okay. If we have 6 elements or symbols here, distinct symbols here, so we are going to have this many 2 permutation or 2 cycles. Okay. So their number, here numbers are even, number is even, but here the numbers 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Here is odd. Okay. So this is going to give us odd permutation. Okay. Here one is single permutation, will not contribute anything. 5. So this is going to be even. Okay. So this order of this order maybe in A6, and from here you will get an odd permutation because there are 4 different element. Okay, and there is single permutation. Okay, so this is going to be odd, and this is a 1. Okay, odd plus odd is going to be even. So this is also going to give you even permutation. Okay, so we have 4, and then we have 5 also. What about here? Here this is 1, and 1 is not going to contribute anything. 4 is there. So if 4 cycle is there, this is going to be odd. Okay. There is 3 cycle. So 3 cycle is going to be give you even permutation. This is even permutation. This is even permutation. A product of even permutation is going to be an even permutation. Here, from here you will be getting this is 2 cycle. Okay. Please do remember this is 2 cycle. This is going to be give us odd. 1, that is one single cycle, and 3, and this is going to give us even. Okay, so even and odd, so this is not possible. Okay, so this is going to be give us odd permutation, odd permutation. Here 3 is single, so this is possible. Of course, 2 times at 2 places we are getting 3, doesn't matter. From here 2 to 2, if you take 2, that is one single cycle, one single cycle, one single cycle. Okay, so 3 product of 3 product of 3 2 cycles, not single cycles. Okay, so this is 2 cycle, this is 2 cycle, this is 2 cycle, something like this, A, B, C, D, and E, and F. Okay, something like this. So this is going to be odd permutation. So from here I can't say anything. There are 2, so this is possible. Okay, and then we have this one, all single permutation. So there is absolutely no problem. This would be this is going to be an even permutation, because identity is an always even permutation. Okay, so possible order for possible orders of elements in A6 are, let us see green circled portion. So we have 1, we have 2, we have 3, we have 4, we have 5. Okay, so these are the possible orders of elements in A6. Okay, do you have any doubt until now? Okay. Similarly, you can find out maximum order here in A10. Okay, in A10 you can find out maximum order. So how will you find the maximum order of this? You can write down partition of this. Okay, so 10, you can write 10, and then you can write 9 1, and then you can write 8 1 1. Okay, you can write 8 2, 7 1 1 1. Okay, and then you can write 7 3. Other partitions, what are other partitions we have? 7 3, we have written 6 4 6 4, and then 6 2 2, 6 2 1 1. Okay, 6 1 1 1 1, and then we have 6 3 1, and continue like this. Okay, so he is talking in this question, they are asking for maximum order. So of course, for maximum order of element in A10, we need to see them, what is the possibility of order. Okay, so if you take this one, if you have some permutation sigma C1, and this I'm writing as product of 2 cycle, and we are considering this one. Okay, so this is of order 6, this is of order 4. Okay, and then a product of these two, that is sigma, order of sigma is going to be LCM of 6 4. So what is the possibility for this? 6 4, I think 12. Okay, this is going to be give us 12. So similarly, if we are looking at here at this element, and suppose this is sigma 1. Okay, so order of sigma 1 is going to be LCM of 6 and then 2, and of course this is going to be what? 6. Okay, so as we move ahead, and here if we are seeing, so here we will 6 6 again. Okay, so similarly we will continue. So as we go upward, we will get maximum. Okay, so here we have order 10. We have order 10, but we need to see. But here we have 12. So it may be, we can guess this, the order may be 12, but we need to see here also the order of the element. Suppose this is a delta. Okay, delta is C1 and C2, the product of 2 cycles. C1 is of order 7, and C2 is of order 3. So order of this delta is going to be LCM of 7 and 3. 7 3 कितना होगा? What would be this? 21. So until now we got maximum 21. And similarly, if you take these two, 8 and 4, of course you are going to get 8, and then 4 8, and then here if you are taking this one, you are again going to get 8, and here you are going to get 9, and here you are going to get 10. So as we see that the maximum order of elements in 8 10 is 21. Okay, this case 21. So this is the way how you can analyze. Of course, I think I kept it question number 10 two times. Okay, and then question number 11. This is the last question for today. Determine whether the following permutations are even or odd. So it's easy. You can split them in form of product of two cycles. Okay, so we can write 1 5 and 1 3. So this is going to be even, and because this is 4 cycle, this is going to be odd. This is a 5 cycle, so this is going to be even. Okay, now you can see this one. So you have here single cycle, and then this is odd, this is odd. Okay, odd cycle, odd, that is odd permutation, not odd permutation, but odd length permutation. Okay, so from here you can write it, then split in two parts. You can split in two parts, and this is one in one part. This is going to be odd, because you can write this like this in the form 1 1 2 1 4 1 3 and 1 2 and then 1 5. And uh, don't try to, if at all, sorry, if you want to simplify this also, suppose of course disjoint cycles commute. Okay, but if you see that here is 1 2 is there and 1 2 is there, something is there, so they will be disappearing together. At least two cycles will be disappearing together. Just we have seen in case of when we were proving that identity permutation is an even permutation. Okay, but thing is that in one step you are going to remove two cycles. Okay, so that will not affect if it is odd, then it will always be odd. If it is even, then it will always be even. So here you can see 1 2 3 4 5. So this is odd permutation. What about this? This is going to give us 3 2 cycle, and this is going to give us 4 2 cycle. This is also going to be odd. Okay, so this is how you can this is how we can determine the nature of permutation, whether it is even or odd. With this, I will stop now.
Thank you for watching this video. To stay updated, please subscribe to our YouTube channel, Cosmos Learning. Happy learning through Cosmos Learning. To watch more, click on any of these cards. Thank you once again.